All right, so let's continue on and talk about the rules of probability. So let's say we have a sample space S and two events, E and F. Okay, now you probably already know some of these rules, or you could deduce some of these rules from the previous lecture. Okay, so here are some properties of the probabilities of these events in the sample space. So property 1 just says that the probability of an event, E, is always positive. It's greater than or equal to 0. So probabilities are always positive. Now we already said probabilities were between 0 and 1. So that seems redundant to me. So property 2 says the probability of the sample space is 1. So that's just saying that the probability that the outcome is going to fall within the sample space is 100%. Okay, that seems kind of obvious too, that if our sample space is complete, that's the set of all possible outcomes. So probability is 1, right? And property 3 says that if the events are mutually exclusive, then we can add the probabilities. Now, in the previous lecture, we talked about the simple events, okay? That we could take the union of two simple events and add the probabilities. So this is just a little more general, that if we take any two mutually exclusive events, then we can just add the probabilities, okay? So again, this only holds if the events are mutually exclusive, though, okay? So remember, mutually exclusive means that the events cannot happen at the same time, okay? If you represent those events as subsets of the sample space, they have no outcomes in common, okay? So if we could draw a Venn diagram of that, so if we have event E and we have event F, okay, so this is E and this is event F, okay, we represent them as sets, and we're going to draw a box to represent the whole sample space, because the sample space is our universal set. Now, this is not correct, right? Because that shows them overlapping. So, but if they're mutually exclusive, there's nothing in the overlap. So we should probably actually draw it like this. All right, we have event E and event F, and they do not overlap. Okay, so these are, oops, not E and E, E and F. All right. So, oops, okay. So this is what mutually exclusive sets look like. We could draw it either way, actually, but mutually exclusive events, for mutually exclusive events, the intersection is 0. So E intersection F equals 0, which means that there's no possibility that we have E and F both happen. Okay, so it's probably a better way to draw it that way, to draw the second way. Okay, so let's keep going here. Now this example is very, very, very much like the examples we did in the last section. So, you know, just like we did before, we can add probabilities if the events are mutually exclusive. So if we're interested, I'm going to say in the probability that X, now that you see here they called the probability the score X. So we're looking for X greater than 400. All right, so I didn't actually read the problem. So this is a bunch of SAT scores for a particular metropolitan school district, and so the score distribution is shown here with the corresponding probabilities. So these probabilities are just the relative frequency of those ranges of scores. Okay. So if we want the probability that someone scored greater than 400, then we can take a look at, okay, 400, that's right here. And so it looks like, so this is 400 to 500, 500 to 600, 600 to 700, and then 700 and above. We want all of those scores. All of those scores are above 400. So all we have to do is add up those probabilities. So 0.23 plus 0.19, 0.19 plus 0.07 plus 0.01. We add that all up and it actually comes out to 0.50. Okay, so that's the probability that someone scored greater than 400 in this district on their SAT. All right, so let's take a look at the next problem. Next problem is asking what's the probability that someone scored less than or equal to 500. Okay, so again, we're going to find 500 and we want everything less than that. So 500 to 400, 300 to 400, and then 300. So we want these last three, and we'll just add them up. So we have 0.23 plus 0.31 plus 0.19. Add those all up, and I got 0.73. So that's the probability of scoring less than 500. And part C asks for the probability that the score is between 400 and 600. So again, we're just going to look at our table, find those probability ranges, and then add them up. So looks like we want to add up 400 to 500 and 500 to 600. So 0.23 plus 0.19 gives me 0.42. All right, so that example is no different from what we did in the last section. All right, so we can add probabilities if the events are mutually exclusive, but only if the events are mutually exclusive. Okay, if they are not mutually exclusive, then we have to account for the fact that those events overlap in some way. And so we have a different formula, but this formula should look familiar to you because it kind of looks like the formula that we had in chapter 6 when we talked about overlapping sets. Okay, so the formula you probably remember is that the number of elements in E union F is equal to the number of elements in E plus the number of elements in F minus the intersection, the number of elements in E and F. Okay, so that's the formula we had before, and I told you don't memorize it because we can just reason it out with a Venn diagram. And we're going to do the same thing here. Okay. I don't think it's necessary that you memorize this formula because we can visualize it with a Venn diagram. Okay, so really all they've done now is just if we take all these numbers of elements in these events and we divide by the total number of outcomes, right, then we'll end up with the probabilities. Okay, so again, so like I said, I don't think you need to memorize that formula. But let me show you how we can use it. In this example, we have an experiment consisting of selecting one card at random from a standard 52 deck. And we're going to let E be the event that an ace is drawn. Okay, and we're going to let F be the event that a spade is drawn. Okay, so we know there's 52 cards in the deck. Let's just make a Venn diagram of what's happening here. So I have two events. I'm going to draw a circle to represent the event E and another circle to represent the event F. Okay, and then my universal set is the whole sample space of this experiment of just drawing a single card from a deck of 52. Okay, so there's 52 possible outcomes. There's 52 ways that I can draw a card from a deck of 52, right? So there's 52 different cards. All right, so let's think about the first event is drawing an ace. How many aces are in a deck of cards? Well, there's ace of hearts, ace of spades, ace of diamonds, ace of clubs. So there's four. There's four aces in a deck. All right, event F is the event of drawing a spade. How many spades are there? Well, there's ace through 10 and then jack, queen, and king. So that's a total of 13 spades. Okay. Now, the intersection here is drawing an ace and a spade. Now we're not drawing two cards, we're drawing one card that is an ace and a spade. So the intersection here is just the ace of spades. And there's only one of those cards. All right, so I'm just going to put a 1 there because there is one ace of spades. All right, so what does that mean? We can do this just like we did in chapter 6. There have to be then 3 cards that are aces but not spades. There have to be 12 cards that are spades but not aces, right? If we add those up, I'm just going to write this off to the side, the union E of E and F, right, the number in the union of E and F, is just going to be 3 plus 1 plus 12, okay? So 3 plus 1 plus 12, which is 16, right? There's 16 total cards that are either ace or spades or both. Okay. I think I just answered, well, I answered one of the questions down here, but that's okay. All right. So if we wanted to know how many are outside of the union, we can just take the 52, subtract the 16, and we end up with 36 cards out here that are neither ace nor spades. Okay. All right. So what is the probability of the event E? What is the probability that we draw an ace? Well, there's 4 cards out of a total of 52. All right. And we can reduce that to 1/3. All right. What is the probability of drawing a spade? There are 13 spades out of 52. And we can reduce that to 1/4. So there's a 1/4 chance that we draw a spade. All right. So what is the probability? This is asking what is the probability that we draw an ace and spade? Okay. Not 2 separate cards. One card that's an ace and a spade. Okay. So there's one of those cards. There's one ace of spades out of 52. So our probability of drawing the ace of spades is 1/52. I guess I can't. I don't need the equal sign because that's us. We can't reduce that. And then what's the probability of drawing an ace or a spade? Okay. So we could draw an ace, we could draw a spade, or we could draw the ace of spades. Any of those. Well, we already know there's 16 elements in the union out of 52. And when we reduce that, we get 4 out of 13. Okay? So, like I said, don't worry about the formula if you visualize it with a Venn diagram. I feel like it's much easier. All right? So, also in chapter 6, we talked about complementary counting. So, when we do complementary counting, we count the opposite of what we want and subtract from the total number, right? So this is just doing the same thing with probabilities, right? The probability that something happened will be 1. So this is the probability that, this is like the probability of the sample space. This is basically P of S, right? And then we subtract the probability of the opposite thing from what we want, and then we'll get the probability of what we're actually looking for. So, okay, let's look at an example. What's the probability when selecting a card from a standard deck of 52 cards? What's the probability that you will not draw an ace or a spade? So neither ace nor spade. Okay, so neither ace nor spade. There's a couple different ways. We could just go straight, since we already have it calculated up here. We know that there are 36 cards. I'll bring this down a little bit. We know that there's 36 cards that are neither ace nor spade. So we don't have to use complementary counting for this. We could just calculate it directly since we already calculated it. But, so let me write out what this is. So probability that it's neither ace nor spade. So I'm going to put a complement so that's not ace or spade. Okay. The other way we can do it is take 1 minus the probability that we get an ace or a spade, which we calculated up here to be 4/13. So we can take 1 minus 4/13, and we'll get 9/13. Okay. Now we could have done it, we could have just said, okay, we have 36 cards that are not ace or spades, and out of 52. Now that also gives you 9/13 if you reduce that. So you can do it either way. But just keep in mind that if we subtract from what we don't want from 1, we get what we do want. All right. So let's keep going here. All right, here's just another example. And again, this should look very familiar because this looks like the type of problem we were doing in Chapter 6. And in Section 6.2 when we were looking at the number of elements in a set, right? So you can see that, okay, so we have, in this problem, we have a manufacturer of kitchen appliances is advertising, and they advertise in Good Housekeeping and Ladies' Home Journal. And then they surveyed their customers. They surveyed 500 customers to find out where they learned of their products. Okay, some of them learned of the products from Good Housekeeping, some learned from Ladies' Home Journal, and some learned from both magazines. So, all right, so let's just set this up like we did before with these Venn diagram problems. All right, we have a set of people who learned from Good Housekeeping, a set of people who learned from Ladies' Home Journal. Okay, and then we have our whole sample space, right? Well, it's not really a sample space because we're actually dealing with numbers of things. So we have 500, this is our universal set of 500 customers that were surveyed. Okay, so now we can just fill in the numbers in the Venn diagram. All right, we know that 140 learned from Good Housekeeping. Okay, now some of those people might have also learned from Ladies' Home Journal about the products, and so I'm going to put it on the line. 130 learned of the products from Ladies' Home Journal, and 80 learned of the products from both magazines. Okay, so those are the people that are in the intersection here. They said, yes, I learned about this kitchen appliance from Ladies' Home Journal, and I also saw it in Good Housekeeping. All right. So now we've got our Venn diagram all set up. We might as well go ahead and fill in the rest of the numbers. So we know that the total number of people in the set G, which is the people who learn from Good Housekeeping, is 140. We have 80 already accounted for here because they also learned about the product from Ladies' Home Journal. So the number of people who learned from Ladies' Home Journal, Good Housekeeping, but not Ladies' Home Journal, has to be 60 because the numbers inside this circle have to add to 140. Okay, and then over here, if we want to know how many people learned from Ladies' Home Journal but not Good Housekeeping, we can just subtract 80 from 130, and we have 50 people who learned only from Ladies' Home Journal, not Good Housekeeping. Okay, so if you add these up, let's look at this. So we have G union L, all right? The number of people that are in the union of those two sets will just be the sum of 60 plus 80 plus 60 plus 80 plus 50, okay? And so that comes out to be 190. So you can see in those two circles, we only have represented 190 people. So that means that 310 people said they didn't learn about the product from either one of those magazines. Okay. All right. So we got to set up. Let's answer these questions. All right. Okay. If you're selecting a person at random from this group that was surveyed, first question is asking what's the probability that they learned about the product from both magazines. Okay. So this is just basically the probability of G intersection L. Okay, that they learned from both Good Housekeeping and Ladies Home Journal. All right, so the intersection is just 80 people out of a total of 500. So the probability is 0.16. All right. The next question asks, what's the probability that they learned of the product from at least one of the two magazines? So either Good Housekeeping or Ladies Home Journal, but at least one can be both as well. So we're looking for the probability of the union of these two sets. All right. We know that there are 190 in the union. We calculated that already. So 190 people learned from at least one of the magazines out of a total of 500. So we get 0.38. All right. And the last question here just asks how many learned of the products from exactly one magazine. Okay. So not both this time. Either Good Housekeeping or Ladies Home Journal, but not both. So in that case, we're just going to, now I could write the set notation. You know, it's G intersection L complement, and then the union of that with L intersection G complement. It's kind of ugly to write. So, but, you know, I think you got exact. I'm just going to write this way, exactly 1 is just going to be 60 plus 50, right? Because those are the people who learned from one of the two magazines only and not both. And again, out of 500. And so we get 0.22 when you calculate that. All right, so this is really no different than those Venn diagram problems we were doing in the last chapter. It's just now that we're working with probabilities, so you're dividing by the total number in this in the sample space. Okay, let's look at the next example. All right, and this is actually one I intended for you to try. So if you want to pause the video and read this problem and give it a try, you can do that now. All right, so this problem's in this problem we've got two dice that are rolled, and we have two events defined. So F is the event that the sum of the dice is 4, and T is the event that at least one die shows a 3. Okay, so we're looking for the sum of the dice is 4. Okay, so let's actually just write that set out. All right, the sum of the dice is 4. All right, well, how can we make 4? We can do a 1 and a 3. We could do a 2 and a 2. And we can do a 3 and a 1. All right, so that's our set. We'll just write it out. What does this set look like? The event that one die shows a 3. So we don't really care about the other die, just one of them to show a 3. So, well, okay, we could do 3, 1. We could do 3, 2. We could do 3, 3. we could do, so that one is actually both show a 3, and it does say at least one. It doesn't say exactly one, so that's fine. 3, 4. We could do 3, 5 or 3, 6. Okay, so those all have the first die being 3. And then we could also look at 1, 3. Right now the second die is 3. Let's look at all the cases where the second die is 3. 2, 3. We already have 3, 3. So I'm going to go on to 4, 3 and 5, 3 and 6, 3. Okay, and I think that's it. So those are all of the outcomes where we have at least one die showing a 3. All right. So, well, we know that the number of elements in F is 3. We know that the number of elements in T is, I can count these up, I get 11. All right. Now, we also know that the number in the intersection is the intersection of these two sets. Okay, where at least one die shows a 3, and they add up to 4. That's just going to be these two cases, 1, 3 and 3, 1. Right? So the intersection has just 2 elements in it. All right. Now we can put this in a Venn diagram. So this is again where you could use the formula that I showed you here to calculate this out, but I like it visual. So I've got these two events. I've got F and I've got event T. Okay. And here's my Venn diagram. I know there are 3 elements in T. I know there's 11 elements in F and 2 elements they have in common. Okay, we have a total of 36 outcomes when we roll a die. Okay, now we can go ahead and fill out the rest of this Venn diagram. So there has to be one event that gives a sum of 4, but it doesn't have a 3 involved. And then there has to be 9 outcomes where one die shows a 3, but they don't add up to 4. Okay, so in the union, F union T, and I can say the number in F union T, it's just going to be the sum. It's just going to be 12. 1 plus 2 plus 9. All right. So, all right. So we're asked to find the probability of either one of these events occurring. Either the sum is a 4, or at least 1, 3 is showing. Okay. So we're actually looking for the probability of the union of these two sets. Okay. So the probability of F union T is equal to the number in F union T over the number of outcomes, so S. So we have 12 out of 36, which is a 1/3 probability. Okay, so 12 is the number in the union, 36 is the total number of outcomes. Alrighty. Alright, so there's one more in this section. I'm going to go ahead and scroll down. This is another problem that you can try on your own. And so feel free to pause the video and try it on your own. And then I will continue to go through this problem with you. So when you come back. All right. Okay, so what do we got here? The probability that this weekend will be cold is 0.6. The probability that it will be rainy is 0.7. The probability that it will be both cold and rainy is 0.5. What is the probability that it will be neither cold nor rainy? Okay, so this is slightly different from the other problems because we're not given numbers now, we're given probabilities. But let's set this up as a Venn diagram. Okay, we've got outcomes where the weather is cold. I'm just going to actually write it so it's a little more clear. And we have outcomes where it can be rainy. Okay. We know that the probability of being cold is 0.6. Okay. So now rather than numbers, we're dealing with probability, which we can do because, you know, the probability is just the number of outcomes of that event divided by the total number of outcomes. So if we just divide everything by the total number of outcomes, we're just dealing with probabilities. So the probability that it's raining or that it would be rainy is 0.7. The probability that it's both rainy and cold is 0.5. So, okay, let me draw the sample space here. So this is all the possible outcomes. 100% chance that an outcome is going to occur, right? Some outcome is going to occur on the weekend. So, what's the probability that it's cold but not rainy? Well, they have to add up to 0.6. So this is just going to be 0.1, right? So everything inside the circle adds up to 0.6. So this has to be 0.1. Everything inside the rainy circle has to add up to 0.7, so this has to be 0.2. Okay? Now you can see the probability, let's just write that out, the probability that it's cold or rainy is going to be the sum of the numbers inside the circles. Okay, so we got 0.1 plus 0.5 plus 0.2. So the probability that it's either cold or rainy or both is 0.8. But that's not what the question asks. The question asks, what is the probability that it will not be cold or rainy? Okay, so we want to count the complement. All right, so the probability that, okay, so cold or rainy, put parentheses around that, oops, and put complement, because I want it to not be cold or rainy. I'm interested in it not being cold or rainy. So I can just take 100% chance that something's going to happen, so probability of 1 minus the 0.8, right? That's the probability of being cold or rainy. So if it's not cold or rainy, then it's it's not cold or rainy, I guess. So we can subtract the 0.8 from 1 and we get 0.2. So the probability of not being neither cold or rainy, okay, being neither cold or rainy is 0.2.